of beginning with a very short introduction of the speaker, and it's a great honor to introduce Tom Kennedy, who is an academic sibling of mine as a former student of David Bridges. He's known for his works in mathematical physics, particularly many which I've personally taken a lot of inspiration from, and also his simulations of SLE, self-voiding walks, and so on. And today we're particularly happy to hear about this very interesting approach of tensor network renormalization. Yeah, please go ahead.
Okay, thank you, Roland, for that very kind introduction. So I was going to give this talk using my tablet. My tablet is going on strike today, so let me adjust this just slightly. So here's an outline of what I want to talk about. So when I get to the new stuff, actually, sorry, let me start by thanking the organizers for the chance to speak and thank all of you for coming. So when I get to the new stuff, I'll be talking about joint work with Slava Rychkov, who I believe is here. And I will start with a sort of quick review of a very old problem. This is almost half a century old now, what I'll call the Wilson-Kadanoff renormalization group, or often it's called the real space renormalization group. So that's mainly historical and sort of motivation and context for what I want to go on to. And that's tensor networks, excuse me. So I'll explain what a tensor network is and how it's connected to spin models like the Ising model. And then I'll look at the sort of simplest renormalization group map you can do for tensor networks and start by asking if the high temperature fixed point is stable. It turns out it's not for that very simple map. I'll give a brief idea of why. And then I'll introduce a better map by introducing something called a disentangler. And the main result in our paper is a proof of the stability of the high temperature fixed point for that better map. So I should say that, of course, the real goal here is to show there are non-trivial fixed points in these tensor network renormalization groups. What I'm talking about is a very modest first step towards that goal. Most of the numerical work, in fact, all the numerical work on tensor network renormalization group has to do a truncation because you're going to put it in the computer. And part of our motivation was to see if you could actually do something rigorous where you don't truncate the map. You work in an infinite dimensional space of tensors. So that's sort of where I'm headed. So that's the preprint with Slava right there. And feel free to interrupt me with questions at any point here. Okay, so going back, like I said, half century. So let's take an Ising model, meaning the spins just take on plus or minus 1 values. So the simplest Hamiltonian would be just a nearest neighbor Hamiltonian. But I want to think about, can you see my pointer when I do that? Probably not. Anybody, do you see the pointer if I do that?
Yeah, yes. Yeah, we can see it.
Okay. So I want to think about a more general interaction where I have nearest neighbor, next nearest neighbor, plaquette, sort of everything. So you'd have a sum over all finite subsets of the lattice. You'd have a coefficient for that subset, and then the product of the spins around that subset. So that's sort of the most general Hamiltonian you could write down. And you need to do that because the renormalization group map is going to immediately take you into that very general space of Hamiltonians. Okay, so Kadanoff's blocking transformation is the following. You take your lattice, here I've got a square lattice, and you divide it into blocks. In the picture, there are 2 by 2 blocks. So the blue dots here are the original spins, the original Ising spins. And then in each block, the red dot is a new block spin variable, which only takes on the values plus or minus 1. So let me emphasize that because there are RG transformations where you let the block spin be the sum of the spins on the block, and then the block spin would evolve to a continuous random variable. Here I'm keeping the block spin to only take on 2 values. So I'm staying in the class of Ising models. Okay. So how do you do that? So you need to introduce what I'll call a kernel. A popular example of that is something called majority rule. And the only thing this kernel really needs to do is satisfy this property, that if you fix the original spin configuration and sum over the block spins, you have to get 1. So in some sense, the original spin configuration needs to be spread out, excuse me, among the block spin configurations in this way. So what's majority rule? it's easy to state if you have an odd number of spins in a block, namely this kernel is either 0 or 1. It's 1 if in every block, the block spin agrees with the majority of the original spins in the block. If you have an even number of spins in the block, you have to figure out what you're going to do in the case of ties when you have an even number, when you have the same number of pluses and minuses in the block for the original spins. But it's easy to find something reasonable there. Okay, and then the renormalization group transformation formally is defined by this equation here. So I take a block spin configuration, I sum this kernel times the usual Gibbs weight, and that gives me e to the minus the renormalized Hamiltonian on that block spin configuration. Okay, now that's a nice equation, but it's formal because there's an infinite volume limit here. Okay, you really need to take an infinite volume limit, and there's no obvious way to do that. So there's no small parameter or anything. So that's a problem. Okay, okay, so there was this condition on Z, sorry, condition on R, condition on T, which was this condition here. And why is that condition imposed? So if you look at the definition of the map and you sum both sides over the block spin configuration, sum over sigma bar. Remember, sigma bar is the block spin configuration, sigma is the original spin configuration. So if I sum this on sigma bar, on the left side, I just get that. On the right side, when I sum this on sigma bar, I get 1, no matter what sigma is. So I recover the partition function of the original Hamiltonian. So the partition function for the renormalized Hamiltonian is equal to the partition function for the renormalized Hamiltonian. Okay, so you can get the free energy of the original system from the free energy of the renormalized Hamiltonian. And then the idea is that you study the critical behavior of the system by studying iterations of this map. So this script R is the map that sends H to H bar. Okay, and of course, that's a non-trivial story as to just how you do that. I won't go into details there. But again, remember, this map is not even defined from a rigorous point of view. Okay, now, the conventional wisdom is this picture here. This is by no means a theorem for this map I'm looking at, but it's supported by numerical evidence to some extent. So there's supposed to be a stable manifold. In my picture, that's the red line. So this is a manifold in the space of all the Hamiltonians, and it's supposed to have codimension 2. So it's not a line by any means, but I can only draw a picture in 2 dimensions. And the eigenvalues of the linearization of this map around the fixed point. So this X here is the fixed point. And the eigenvalues of that linearization are supposed to determine the critical exponents. So this point right down here would be the critical nearest neighbor Ising model. If you start exactly at that point, you will flow along this stable manifold to that non-trivial fixed point. If you start a little bit off, you'll follow the stable manifold for a while and then diverge and either head towards the high temperature fixed point or head into the low temperature region, depending upon which side you start on. Of course, this is a discrete time map, so to speak, so you're not literally flowing, you're sort of jumping along in discrete steps as you iterate this transformation. I'll pause and see if there are any questions because I'm going kind of fast. Okay, are there any rigorous results on this map? Not much. If it's very high temperature or large magnetic field, then you can prove by what are now fairly standard high temperature expansion methods that the map is defined. So these are fairly old references. If you look at low temperatures, so if you go well below the critical temperature, then Griffiths and Pierce observed some time ago that the map can have problems, and Van Inter, Fernandez, and Sokol actually proved some theorems that show the map is not defined if you're well below the critical temperature for various choices of the kernel T. And there are even some kernels for which you can show it's not defined near the critical temperature. But there are essentially no rigorous results that say the map is defined near the critical surface, even if you just look at the first iteration of the map. And just an editorial remark here, the goal should not be to look at every possible kernel and see whether it works or not. The goal should be to find one kernel that does work. Okay, numerical studies, there are of course a million of them. Interestingly, one of the first numerical studies was by Wilson in this very famous Reviews of Modern Physics paper. This is the paper in which he applied the renormalization group to the Kondo problem. but it also has a section on exactly this problem. And he did a computer computation in which he kept 217 terms in the Hamiltonian. And I put an exclamation point there because this was 50 years ago, almost. So, you know, his computer is quite a bit different from my computer. Unfortunately, it's very hard to figure out exactly what he's doing. It's fairly ad hoc and there's not much detail. In fact, he starts his description of what he did with this sentence here. So I can't really figure out how to reproduce what he did there. There have been lots of Monte Carlo studies of this map. In particular, Robert Swinson introduced an idea where you can find the linearization of the map. That is, you can find the eigenvalues by looking at correlation functions instead of the map on the space of Hamiltonians, which was a neat idea. It had the unfortunate side effect that you don't compute the map as a map on the space of Hamiltonians. There's some interesting papers by these three authors where they were computing the map. And one thing they emphasized was that you see significant dependence of the renormalized Hamiltonian on just how you truncate this thing. You've got to truncate somehow to put it in your computer. And what you'd like to see is that things are fairly stable as you remove that truncation. And they're not that stable. So there's a quote from their paper there. So they make the point that even though the 4 and 6 body interactions may have smaller coefficients, there are a lot of them, and because of that, they may actually be as important as, for example, the 2-spin interactions. Okay, so a little over a decade, I did some numerical studies of this as well, and I want to show just one plot quickly. I need to move on. So it turns out that if you go to lattice gas variables instead of spin variables, you can do some really accurate computations. So lattice gas variables are just variables that take on the values 0 and 1. They're related to the spin variables by that equation. And you can write down the renormalized Hamiltonian again as a function of the lattice gas variables like this, very similar to what you do in the Ising spins. So what this computation did was you take the critical nearest neighbor Ising, and you can compute these coefficients extremely accurately. I won't go into how you do that. It's not a short story. And I computed about 10,000 of them. And then you order them in decreasing absolute value, and you just plot those points as a function of where they are in the order. Okay. And here's the plot. So this, again, the axis down here is just, the first coefficient, second coefficient, third on up to about, well, the 10,000th one is off this slide. And the bottom curve is what I want to start with. So these are the coefficients in this order. And the vertical scale is logarithmic. So this is exponential decay, this straight line, which is great, okay? Except when you compute the slope. So the blue line is a fit using this form. So in other words, if you want to see this coefficient go down by a factor of 2, you have to go about 800 coefficients further down the list. Okay, so it's decaying exponentially, but extremely slowly. And the top curve is sort of a cumulative sum of this, so to speak. So if I look at a point on the top curve, it's the sum of the bottom curve all the way out. Now it looks like this thing is falling off very fast at this point. That's an artifact of the number of coefficients computed. So if you were to compute 20,000 coefficients, this curve would go a little farther out and then start to fall off as it gets close to 20,000. So I think the true curve is actually doing this forever, so to speak. Okay, so that's quite discouraging if you want to actually do something rigorous with this map. Of course, what you really want to do is prove there's a Banach space of Hamiltonians and a rigorously defined map on it, which has all the usual stuff, a non-trivial fixed point, stable manifold of codimension 2. I'd be very happy to see just a systematic numerical approach to computing this map. And what I mean by that is basically a code, an algorithm, which has a truncation parameter or maybe several truncation parameters. And so that as you vary those parameters and remove the truncation, you would see that the coefficients you're computing for the Hamiltonian converge very nicely. And you sort of have real control on the truncations there, so to speak. So I can do that for this first step where you start with the nearest neighbor Hamiltonian, but I certainly don't know how to do this if you want to iterate the map. Okay, so this paper up here, I looked recently, it's got a whopping 6 citations in Google Scholar. One of those is mine, so it really has 5 citations. But it did have one nice effect, and that is that Slava noticed it, and he got in touch with me, and that led to a very interesting series of Zoom meetings and discussions that led to the work that I want to start headed into now. But I'll pause because I'm changing topics here. So any questions at this point? Okay, so what's a tensor network? So what's a tensor? So I take a real Hilbert space, could be finite or infinite dimensional, and a tensor is just a multilinear map from some number of copies of that space into the real numbers. Usually you think of the tensor in terms of its components. So the IJKL component here is given by that. I'm thinking of a tensor of order 4 here. You could do a tensor of any order, but I'm going to work on the square lattice, and the tensors will be 4-legged tensors, so to speak. And the network is the following. I take a whole bunch of copies of this tensor. So every box is another copy of this tensor A, and then I contract them. So what does that mean? So for every line like this, it means that I put the same index on this, the leg of this tensor and the leg of this tensor, and then I sum over that index. Okay? And I do that all over this network, and I impose periodic boundary conditions. So this leg is connected to this leg. So when I'm done contracting this thing, I just have a number. All right, so these things have a long history of use to study condensed matter systems. You can use these things as approximations to the wave function, to the ground state of a condensed matter system. Lots of work in that application of tensor networks. You can also use them to represent classical systems like the Ising model. So here's a picture to show how you do that. So the Ising model here has been rotated by 45 degrees. So the red dots are the Ising spins, and the red lines are the lattice for the original Ising model. And then I define a tensor A by this formula. So the Ising spins are living on the bonds in the tensor network. And this tensor, as a function of its 4 legs, is given by this formula. So it's e to the beta times the sum of the 2-body interactions between those 4 spins. And if you stare at this for a minute, you see that contracting the tensor network just amounts to the sum over the Ising spins that gives you the partition function of the Ising model. Now, because of the rotation by 45 degrees, the boundary conditions are a little strange, but there are other ways to represent the Ising model and get sort of more normal boundary conditions. Okay, but the takeaway here is you can turn the Ising model into a tensor network. Let me note briefly, there's some sort of hidden symmetry here. If you take your tensor A, you can do what you might call a gauge transformation. You can multiply it by an invertible matrix G on one side and G inverse on the other side, call that new tensor A twiddle. And the contraction of the A twiddle network will be the same as the contraction of the original A network, for the sort of obvious reason that if you stick two of these things together, you'll have a G and a G inverse, which will cancel out. Okay. All right. So here's a really simple renormalization group for that tensor network. I don't believe this exact map appears in this paper, but this was the first paper that looked at doing this renormalization group for classical spin systems using tensor networks. So what's the simple map? So I take 4 copies of A and I contract them together like this. So that gives me a new tensor which has 8 legs. And if I'm working on an infinite dimensional Hilbert space, then the Hilbert space tensor with itself is isomorphic to the Hilbert space. So in other words, I can get an isometry that essentially takes 2 legs to 1 leg, and I'm calling that J here. So J is a map from H tensor H back into H, and if I add copies of J to the 4 double legs here, then I can turn this tensor back into a 4-leg tensor. Okay. And that's my map. So the renormalization group map here is I send A to this A prime. Okay, and let me just note, there's a ton of freedom, of course, in how you choose that J. There's no sort of canonical way to do that. But let me note that if you fix the J and then apply a gauge transformation after this renormalization group map, you recover all possible J's. So the sort of freedom in the choice of J also can be thought of as a freedom in the gauge transformation. Okay, why do we think it's worth looking at these things? Well, if you look at the Wilson-Kadanoff renormalization group, it has the nice property that the spin stays fixed to be just plus or minus 1. But the Hamiltonian gets very complicated. In fact, after one step, it's immediately has infinitely many terms. It's non-local. You have many body terms of all sizes, hopefully with some decay. By contrast, for the tensor network renormalization group, the tensor stays local. It's always a tensor with 4 legs, but the leg dimension grows. Okay, obviously, if I did this with a finite vector space, then these legs, the dimension would be the square of the dimension that I started with. So you really have to work in an infinite dimensional leg space, so to speak. On the other hand, there's a real advantage, we think, to the tensor network approach, which is that it's very computable. So remember, with the Wilson-Kadanoff approach, there's sort of no obvious way to compute this thing. There's an infinite volume limit you have to take. There's no small parameter. What do you do? So the map I just showed is very computable, trivially computable. It's going to turn out to be too simple. We have to do more complicated maps, and we have to introduce something called disentanglers, and that complicates how you would compute this map, but it's still much more computable than the Wilson-Kadanoff blocking map. Okay, so as I said, what we really want to understand is what happens for non-trivial fixed points, but we started with a much more modest project, namely looking at the high temperature fixed point, and in particular seeing if it's stable or not, and seeing if you can prove things without truncating like you always do in the numerics. Okay, so high temperature fixed point. So you could go back to that slide where I mapped the Ising model to the tensor network, and you could set beta equal to 0 and see what the tensor is. This is not that tensor. So the tensor I'm going to use is the tensor where there's only one non-zero component, the 0, 0, 0, 0 component, and I'll take its value to be 1. So all the other components are 0. This thing is gauge equivalent to the tensor that comes out of setting beta equal to 0 in that previous slide. I'll leave that as an exercise. Okay, now I claim that if I take a j with this property, which by no means determines j, but I'll impose that property, then this thing is a high temperature fixed point. And so I was hoping on the tablet to be able to draw some pictures here. Let me see if I can draw pictures. It will be really crude. So I'm going to represent the high temperature fixed point just by a tensor x with a dot right here. Okay, so that's my high temperature fixed point. And if I contract 4 of those things, I'm just contracting 4 of those. And then because this is this high temperature fixed point, there's a 0 on every bond you see. So there's zeros everywhere. And then if you have this property on the map, what's going to come out of this is the tensor, apologies for the horrible drawings, where you have a 0 here because 0, 0 is getting mapped to 0 like this. So trivially, this thing is going to be a fixed point of that map. Okay, is it stable? So by stable, I mean that if I take this thing and I add a small perturbation and I do the map, do I get back this high temperature tensor plus an even smaller perturbation? So I need a norm if I'm going to talk about the size of these tensors. And we're going to use the Hilbert-Schmidt or the Frobenius norm. So the norm squared of a tensor is going to be the sum of the squares of all its components. That's a nice norm. It's invariant under these gauge transformations. And more importantly, it plays nicely with contractions. So if I take 2 tensors A and B, and I contract some of their legs and get a new tensor C, then the Hilbert-Schmidt norm of C is bounded by the product of the Hilbert-Schmidt norms of A and B. And you can apply that many times. So for example, if I look at this contraction of 4 tensors, call that T, then the Hilbert-Schmidt norm of T is bounded by the Hilbert-Schmidt norm of A raised to the 4th. Okay, so it's a nice norm. Okay, so now I really need to draw a picture. So I want to do perturbation theory. So I want to think of my tensor as now being this high temperature tensor, this high temperature fixed point, plus something, and I'll try and draw a circle here. So this is my perturbation. So my tensor is high temperature fixed point plus perturbation. And I want to contract 4 of those. What am I going to get? Well, I'm going to get a term where I contract 4 of these. That just gives me back the high temperature fixed point. And then the first order term, there are going to be 4 of them. And what will they look like? They'll have the high temperature fixed point on 3 of the vertices. And then on the other vertex, there'll be the perturbation. So there'll be a perturbation here, high temperature fixed point on all the other places. So what have I got? I've got zeros in lots of places. I've got zeros on all the legs coming into a high temperature fixed point. So in particular, I've got a 0 there and I've got a 0 index there. And then this index can be anything. So I'll just call it X. And I get a diagram like that. Okay. So the piece of the perturbation where these 2 indices are 0, but these 2 indices are not, that piece is not getting made smaller in any sense. Okay, just sort of, as you iterate this, it just sort of goes along and doesn't really change. Now you can do this much more carefully. You can write down sort of very specific perturbations and actually set up the J so that you get a perturbation which is an eigenvector of the linearization around this fixed point with eigenvalue 1. So this is called the corner double line problem because the usual diagrams people use to represent these things have sort of double lines going through a corner. I'm not going to go into all the detail of that, but hopefully you get a glimpse of why this thing doesn't work. Okay, so how are we going to fix it? So if you look at the literature, there are all sorts of fixes. So here's one. Why is it doing that back on? Okay, so here's one that this is not exactly, well, it's not what we do in the paper, but it's the same sort of ideas and it's simpler to explain. So I'm going to explain this one. So I want to take a contraction of 4 copies of A, and I want to try and write it as a contraction of 4 tensors, which are not all the same. So I'll call them B1, B2, B3, B4. And I want this to be exact. And I want the B's to be better than the A's in the following sense. I want these components of the B's to be of order epsilon squared. Now I need to explain this notation here. So when I write the tensor and I put a 0 on a leg, that means that that leg's index is fixed to 0. When I put an X on it, it means that leg index is anything other than 0. And what this diagram really represents is the tensor whose components are the same as the B1 components whenever the indices meet these conditions. And if they don't meet these conditions, then the component is 0. So in a sense, this diagram is a subtensor of the tensor B1. I hope that makes sense. And when I say that this diagram is order epsilon squared, what I mean is the Hilbert-Schmidt norm of this subtensor is order epsilon squared. Okay, now if you're paying attention, you may think that I've made a mistake. Because if I look at B1, the things that were causing trouble in the perturbation theory were when I had non-zero indices out here, and the condition I'm putting on is that this is small, order epsilon squared, when I have non-zero indices out here and 0 indices up here. Okay, I didn't make a mistake. In the next slide, we'll explain why. Questions on this slide? This is the crucial part of the definition of this map. Okay, it's not at all clear you can do this. I'll have to give you some indication that you can do this. Okay, but why is it a good thing? So here's the magic of this. So I'm going to do this disentanglement in the blue box here. And you should imagine this blue box is repeated. So there's another blue box here and so on. I just didn't want to draw them to keep the figure from getting too cluttered. But then I'm going to contract in the red box. So I'm going to take these 4 tensors and I'm going to contract those 4 tensors, and that'll be my new tensor. Okay, and again, you should repeat this red box. So there's another red box over here and another one below it and so on. Okay, so now if you think back to the property I got on this tensor, remember with B1, I was sort of reducing the size of the components where I had zeros here and non-zero things here. And now you see that that's just what I want to do. Those were the things that were causing me trouble when I contracted these 4 tensors. So if you sort of look at first order perturbation, what's coming out now is order epsilon squared. So you can sort of see that if you could get that disentangler, then this is going to give you a contraction. Okay, so let me pause and state a theorem. So there is a way to define that disentanglement so that you get a tensor RG map, so that if you start with the high temperature fixed point plus a small perturbation, then the image under this map is the high temperature fixed point plus a perturbation, and the norm of the perturbation is bounded by a constant times the norm of the original perturbation raised to the 3 halves. Notice it's 3 halves, not 2. There's sort of some other things that come out of the proof that sort of weaken the result, so to speak. And I should mention that we're always normalizing our tensors so that this 0, 0, 0, 0 component is 1. So if you do Wilson-Kadanoff maps, there'll be a constant term in the Hamiltonian, which of course you might as well take out as you iterate the map. Otherwise your Hamiltonian will sort of grow. Similarly here, you can sort of take out a scalar multiple at each step of the map to sort of keep it normalized, so to speak. Okay, so I want to try and sketch the proof of that. And again, this is just repeating the slide from before of the disentangler. And essentially this idea, and then the following slide where I had the red and the blue groupings of the tensors, reduces the proof to proving that you can do this disentanglement. Now there's a little bit of a cheat in what I'm going to do. If I have time at the end, I'll say what the cheat is and how you fix it. So it's a cheat in the presentation, not in the full proof. Okay, so what's the idea? So take contraction of 4 A's, and let me insert, so U is going to be a unitary, actually an orthogonal transformation. So U inverse is just U transpose. So I can insert this, because of course this product is just the identity. So I'll stick that in between here. And then I'm going to, if I can get back my pen and my great drawing ability. So I'm going to view this as 2 pieces, a left and a right piece. And then I'm going to, so let's just look at the left piece. I can get the things to go away. Sorry about this. Okay, so let's look at the left piece. So if I can show that that left piece is given, can be represented as a contraction of B1 and B4, where B1 and B4 have the properties I want. So remember, for B1, that meant that this subtensor needs to be of order epsilon to the 3 halves. Notice, by the way, that as soon as you put a non-zero index on this thing, the high temperature part of these things is gone. So this is a priori order epsilon. What I want to do is knock it down to order epsilon to the 3 halves. So if I can do that, then I'm in business. I do that on the left side, I do that on the right side, and then I've got my B1, B2, B3. Okay, so I've got to tell you what this U is. That's where all the work is. How do you define a U that does that? So here's the idea. So let me take this diagram. So I've set 4 of the legs to 0. The leg that's being contracted is only summed over, excuse me, non-zero indices. Okay. And then I'm going to call this thing, this number, Mij. So I can use that to form a new tensor. So notice this tensor has the same structure as U. So it's got 4 legs coming out horizontally, just like U did. Okay, so this is a tensor whose non-zero components have zeros on these legs, and then on these legs, these indices have to be non-zero, and the value of that component is this number Mij. Okay, so another way to write this M would be in sort of broad cat notation like this. Okay, and then U is going to be the exponential of minus this M plus its transpose. So as I said, this thing has the same structure as U, so you exponentiate it and you get back a tensor that has the right structure to serve as your U. This thing is skew symmetric, since it's just minus M plus M transpose. So this is an orthogonal transformation. And notice, excuse me, again, the high temperature part of A doesn't contribute to this diagram because I have a non-zero index here, and the I and the J are non-zero. So this diagram is of order epsilon squared because it just has contributions from the perturbation for A here and the perturbation here. So the Hilbert-Schmidt norm of this M is order epsilon squared. And all I really need about this U is that it looks like the identity and then the linear term, and then the rest is going to be order epsilon to the fourth because of this fact. So that's all you need to remember about U. Okay, so now I'm going to look at this thing. So remember, this is what I want to show can be written as a B1 contracted with a B4, and I want to compute this thing just to order epsilon squared. Okay, and remember U, what does it have? It has an identity, and then it has an order epsilon squared part, which is just this. So the only thing I'm going to get when I compute to order epsilon squared is the following. There'll be this contraction of two A's composed with just the identity operator, so that's this term here. Then there'll be the contraction of the two A's composed with this order epsilon squared part of U, this part. But the only thing that's going to matter from the AA are the high temperature parts. Anything else, if I have a perturbation here, that'll be order epsilon squared. And then when you multiply by this, you're up to order epsilon cubed. So the only order epsilon squared terms are basically these two diagrams here. Now, what does this thing look like? Well, it's easy to see that M transpose, when it contracts with this, gives you 0, because M transpose has non-zero indices on this side contracting with 0 indices. And M, when it contracts on this thing, remember M has 0 indices on the left side. So when it contracts with this diagram, you just get back this diagram that defines those MIJs with a minus sign. Okay, so this term is going to give me this diagram, and that's going to cancel. This diagram is a subtensor of this, so this is going to cancel some of the components of this diagram here. Okay, and it's canceling the things you don't like, because it's canceling things that have non-zero indices here and 0 indices here, correspondingly down here. It's canceling the things you don't like. Okay, so if I look at A contracted with A and expand that out, it's got 4 diagrams. There's actually 5 here. Let me say why it's 4. So there's the high temperature contracted with the high temperature. There's the high temperature contracted with the perturbation. And then there's the perturbation contracted with the perturbation. And I'm going to split that diagram into 2 pieces where I put a 0 index on that leg, and then I put a non-zero index on that leg. And I'm doing that because these first 4 diagrams can be very nicely written as little b1 contracted with little b4, where b1 is just this tensor. Okay, so it's the high temperature fixed point plus the part of the perturbation where I fixed that leg to be 0. So if I contract this thing, and of course b4 is the reflection of this guy. So if I contract this thing with b4, I get 4 terms. I get high temperature contracted with high temperature, I get high temperature contracted with perturbation, and so on. And in particular, when I contract perturbation with perturbation, I have a 0 on that internal line. So I get that diagram there. Okay, so that stuff is given by that. And this thing is very nice because this tensor B1, little b1, has the properties you want for capital B1. So this will be part of the capital B1. Okay, now what's left? So what's left is this diagram. And a lot of this diagram is getting canceled by what came from that unitary. Okay? And then there's stuff of order epsilon cubed. Now, the way you deal with the stuff of order epsilon cubed is you think of it as a contraction of an order epsilon to the 3/2 tensor with an order epsilon to the 3/2 tensor. And then you stick those order epsilon 3/2 tensors into capital B1. Okay? So it's because this is order epsilon cubed that I'm only getting an order epsilon to the 3/2 out of my final estimate. Okay, so I've been going much faster than I did when I timed this talk. Are there questions about the proof? I mean, that's basically the end of the cheat version of the proof. And now I want to try and say a little bit about the cheat. Any questions on that? Okay, so what's the cheat? So I sort of very happily claimed that this diagram, pointing the wrong thing. So this is canceling a lot of diagrams in here. And I'm claiming here that what's not canceled is order epsilon cubed. And that's not quite true. So here's a diagram that doesn't get canceled. It's got a non-zero index over here, but another one over here. So that's not getting canceled out. And it's only order epsilon squared. Okay, there's a perturbation here, a perturbation here. That gives you an epsilon squared, not an epsilon cubed. Okay, so the fix is kind of involved. And let me just try and say in words what you need to do. So before we do any of this, before we do this disentanglement and then this contraction, we do a preliminary step where you just do that simple renormalization group map. You just contract 4 things and call that your new tensor. So you should now think of what's sitting here as having come from contracting 4 copies of the original A. Okay, so there's a lot of sort of hidden structure in this thing now. And if you look very carefully at this diagram now, you see from that hidden structure that this diagram is actually of order epsilon cubed in that new way of defining the map. Okay, so a fair number of details there, but that's sort of the idea. So you first do a simple renormalization group map where you just contract 4 tensors that adds some structure to your A, and then you do the disentanglement step, and then you do this red-blue box contraction step. I should also mention that another thing I hid was that before you do anything, you do a gauge transformation to the tensor, and you can make any component that has 3 legs with 0 index and a 4th leg with a non-zero index. You can make those diagrams all be of order epsilon squared. So if you sort of look carefully at things here, I was also using that fact, although it's very well hidden in what I presented. Okay, so I've gone through this way too fast because nobody was asking questions. So Outlook, final slide here. Again, I want to emphasize that our goal eventually is to try and show there's a renormalization group map for tensor networks with a non-trivial fixed point. And what we wanted to do is sort of a modest first step is look at a tensor renormalization group map where you don't do any truncation, where you rigorously control the errors, so to speak, and at least show that the high temperature fixed point is stable into the map. And if you look at the numerical tensor renormalization group maps, there's a whole zoo of them, all of them with acronyms. There's TNR, there's TNR loop, there's GILT, there's all sorts of things. And they're all different in terms of how they do. I mean, they're similar in that they do some sort of disentanglement, but they're different in terms of just how they carry that out. So an important question to figure out, of course, is which one of those is going to be best, not from the numerical point of view necessarily, but from the point of view of actually achieving this holy grail there. Okay, so again, apologies for the horrible drawing of figures here, blame my tablet. And I'm happy to answer questions.
Well, thank you for the great talk. I have a number of questions, but I imagine others too. I'm happy to let someone else start.
Yes, someone start.
Well, maybe I'll start with 1 or 2 questions then. One question is, so this is all 2D, I explained, but I imagine that it's somehow possible to do the same in higher dimensions. Is there a way one can see numerically or so that 4 dimensions it should get simpler, or is it getting more complicated? I mean, because the fixed point is, I mean, in the usual Wilson formulation, the fixed point is Gaussian above 4 dimension or in 4 and above. And is there any way this would show up here? I mean, I understand it's very different, but.
So let me answer that question by first going back to Wilson-Kadanoff. So I don't see how in the Wilson-Kadanoff transformation, if you're in 4 dimensions, you see that the fixed point is Gaussian. I mean, what would the analog of a Gaussian fixed point be in that Ising language? And
yeah, I understand it. But if you, I mean, if you go to the, like, not the majority rule, but the like the formulation where spins become continuous, right? Then you should see a Gaussian fixed point. And I guess in this setting, there's no analog of this, or
Slava, do you want to say anything? Because I know Slava's been working with some other people about trying to do this tensor network working directly with continuous fields. I see Slava, but I don't think he's. You want to jump in, Slava, and say something, or because I have no answer to that question.
Well, I think, no, my personal philosophy is that, okay, there are some fixed points that you know that they exist from various maybe intuitive, non-rigorous ways of reasoning. So I think the first step for rigorous theory is to just try to treat each of these fixed points in some way, with some method, rigorous method. But I think to understand why each fixed point exists is even more complicated. So yeah, I don't pose myself such a high problem. It's really complicated.
So, I mean, you can do this in 3 dimensions, of course, and the numerical people have tried to do it in 3 dimensions, and I don't think they've had much success. I'm not an expert on the numerical literature.
So what I want to say is that, okay, if you're interested in fixed points, then you design some if you're interested in the neighborhood of the Gaussian fixed point, then you design some RG method, which may be tensor or something else, which is kind of tailored for the neighborhood of that fixed point. And then it's not going to be this spin method, it's going to be something else. But if you are interested in a non-trivial fixed point specifically, then you might want to choose this discrete variable method that Tom presented.
Mm-hmm. Okay, thank you.
Tom?
Yeah.
Well, firstly, I thought when you said that the dimension of the Hilbert space on the edges was increasing, I thought in a way that was a way to sneak in the convergence towards, let's say, a continuous variable on the edges. Is that wrong?
I mean, my hope would be that if you get a non-trivial fixed point, it's going to be, if you've restricted your indices to say the first 10,000, that would give you a very good approximation to the fixed point that you've got. If that's not true, this whole program is doomed. But so I would sort of hope that you could choose your J or choose your gauge symmetry so that you could sort of get your tensor to be living in essentially to a good approximation in sort of a finite dimensional part of the index space. And that strikes me as rather different than what you're thinking of.
Well, I suppose one way of saying what I was thinking of is that, yes, it lives in a finite dimensional Hilbert space, but it's embedded in a infinite dimensional Hilbert space, which permits an error outside that finite dimensional one. And that error is under control.
Right. Yeah. But that's very, I don't see how that's related to a sort of continuous field. Maybe I didn't understand.
Well, I suppose, I mean, a continuous view could always look a bit discrete if you used some basis.
Sure. And there's been work like that where people look at something like Pi4 and sort of discretize it by using, I think, a basis of Hermite functions or something. Yeah.
It could be, in other words, it could be, in fact, that it is approaching a Gaussian. Perhaps that's hard to see, but
In higher dimensions.
yeah. Well, I had another question, which is totally different, and that is that Baxter and some co-authors for two-dimensional Ising wrote a paper called the 101st Solution to the Ising Model.
Okay.
And what it was, so this was an Ising model that I think began on a triangular or a honeycomb lattice. It doesn't matter. Maybe it's a honeycomb lattice. And they did a star triangle representation twice. The first one would map it to so let's suppose you start on a honeycomb and then you apply a star triangle transformation. You get a triangular lattice, an Ising model on a triangular lattice, and then you do it again and you go back to your honeycomb lattice, and he noticed that there was one less point. He started with a finite lattice, and he noticed that there was one less point, or they noticed, after you've done that. So if you keep doing that, eventually you end up with a one point Ising model. Now, this is a very general framework that you have introduced with using RG on tensor models like this, and maybe it includes that in some way.
I mean, I think I looked at this paper or some version of it some time ago. I mean, it's a very different, I mean, in that approach, like you say, at each step, you basically reduce a lattice with n spins to a lattice with n-1 spins, right? You're not sort of reducing it by a constant scaling factor each time. Is that? No,
it's kind of an infinitesimal version of your transformation.
Yes, yes. I don't know how that relates to this. So, I mean, as I recall, you get a non-translation invariant Hamiltonian as you do that, right?
Oh, I didn't notice that. I see. That's interesting. Well, I suppose, it must be. Well, I don't even remember what boundary conditions, whether he was using periodic boundary conditions. But if you don't, then for sure.
Yeah, I don't remember the details of that, what they did.
The thing is, it really is an RG transformation, because you could do it a hell of a lot of times until you had half as many sites on the lattice.
Yeah.
And that would be a big, that conglomerated thing would be an RG transformation.
Right. I mean, it would have the problem that if you start putting in a more general Hamiltonian, it's not going to work, right? The star triangle game.
Oh yes, it's rather special, but that's why I'm fascinated by your tensor network, because I guess it's just a way of asking if that is an RG transformation that truly works. I mean, it's rather an odd one, but it truly works.
Yes. But the fact that you only do it for a nearest neighbor Hamiltonian, from my point of view, kind of defeats the purpose, because what you really want to know is that if you take a more general Hamiltonian, you still converge to this fixed point and have the same critical exponents and so on. And you're not going to be able to do any of that with that sort of a map. Right?
Well, that's true, of course. It's just a kind of, I mean, if that is a tensor transformation, I mean, if that is a map, that honeycomb, this thing applied twice, if that is one inside your tensor framework, that's rather encouraging.
Okay. Yeah, I'll have to think about that some. Yeah.
Did you think about the low temperature? Is there a low temperature version of what you're doing?
Yes. So if you look at how you map the Ising model to the tensor network and you send beta to infinity, what you get are two copies of the high temperature fixed point. So you get a tensor that has two non-zero components. For example, A0000 and A1111. So that's sort of a mix of two pure phases, an all plus phase and an all minus phase. And then that combination will, if you iterate the normalization transformation, it'll go back to itself. So then you can ask if that is stable. And I've thought about that a little bit, but not a lot. And there's a Antoine, I'm forgetting his last name, help me out, Slava. Antoine, Slava, who am I thinking of? There's a young guy in Paris working on this problem. I think, I don't know how actively, but
Antoine Tillois.
Antoine Tillois, thanks. So I think it ought to be possible, and I'm not claiming I know how to prove this, but it ought to be possible to show that if you take one of those low temperature fixed points and perturb it, you flow back to that. In fact, our result immediately implies if you take one of those low temperature fixed points and perturb it, you will flow back to that low temperature fixed point. A more interesting question is to take a convex combination of those two fixed points and perturb it a little bit, and then show that you'll flow to one or the other of those two fixed points, and there'll be a sort of critical intermediate point where you'll get stuck at the combination of 1/2 of one plus 1/2 of the other. I'm not saying this very well. So you ought to be able to control this map for a line of Hamiltonians that crosses a first order phase transition. That's what I think. Does that answer your question, Tom?
Yes, thank you.
None of this is done and written down or anything like that, but I think there's doable stuff there. Yeah. Which is in contrast to the Wilson-Kadanoff thing, because if you go to low temperatures with Wilson-Kadanoff, nothing nice happens. You really need to go over to a contour thing and do things like, well, Antti, who I think is here, is very familiar with this. You want to do a renormalization group in terms of contours in the Ising representation.
And what about quantum systems? Is there natural generalization there? It must be, right?
There must be. I haven't thought about that at all. I mean, these tensor networks were originally being used to study quantum systems, so yeah.
What are those two fixed points at low temperature? Because I'm thinking about that in terms of, infinite H positive or negative.
Yes. So
yes, that's that.
So if you go back and look at, let me, when I share the screen again.
Because this is exactly what we were doing with Antti and
Yes.
Krzysztof.
I didn't realize you were here, Roman. I should have said.
But with totally different normalization transformation with this, contour type thing.
So if you go back to how you embed the Ising model in the tensor network, where's that slide? And you add in a magnetic field. So now you have an H times the sum of these four spins. And you take beta very large and you take a tiny H, then you'll pick out, so for example, if you take a small positive H, all these components will be huge because beta is huge. But if you rescale it so the largest component is 1, then you'll get a tensor whose only non-zero component, whose only significant component is when all 4 spins are +1. Okay.
Mm-hmm.
And that's exactly the same tensor as our temperature fixed point. you know, so the fact that that thing is stable is immediate from what we proved for the high temperature fixed point. Does that answer your question, Roman?
Well, more or less, and are you recovering the first order phase transition there on the way? You should go from one side of first order transition, you should go to one fixed point.
I think something can be done there, but I don't claim to have done it. Yeah. So you could look at, so you could look at the family, so take beta very large, but not infinity, and then vary H from positive to negative. So it goes through the first order phase transition and look at the tensors you get, and then apply this map to them. And what you'd like to show is that unless you sit right at H equals 0, you either flow to the plus low temperature. And you'd like to show that even if you add in some perturbation. So if I add in some perturbation that's not spin flip symmetric, then the critical value of H should shift a little bit. It won't be exactly 0.
Yeah.
And my guess is you can prove things there, but I certainly don't claim to prove anything like that. Does that?
Yeah.
Other questions?
Tom,
Hello.
do you have an idea about the anomalous dimensions for correlation?
What are you asking?
Is your method suitable for treating correlations as well or not?
I mean, there's always this problem, even with Wilson-Kadanoff, that you're losing. I mean, you can't write down. If I want to compute a 2-point function in the original model, I can't get that from the renormalized Hamiltonian, right? But the 2-point function in the renormalized Hamiltonian corresponds to something more complicated back in the original model. And I haven't really thought about the tensor networks, but you're losing information, so. I'm not sure how to answer that question. I mean, people, the numerical people have computed not just the sort of usual critical exponents, but other eigenvalues that they then try and match up with what you see in conformal field theory. And I don't know, maybe Slava can comment more on that. But, so there's certainly hope of getting lots of information out of this tensor network transformation. Not just the sort of two, not just the eigenvalues bigger than 1, so to speak.
Thank you.
With the correlation question, one can also imagine just, I mean, in your high temperature context, right, to see the exponential decay of the 2-point function, right? And I mean, the perturbation, naively, it sounds to me like it's the same kind of perturbation you have, except you just do it at 1 point or in one tensor rather than everywhere. And right, if you add a correlation field in one place, it's a perturbation of probably of a similar type as you have, except you just do it.
Let's see, let me see if I understand the question. So I could, first of all, I got to figure out what I mean by a correlation function in the tensor network. So if I start with a tensor network where it's just the high temperature fixed point plus a smart perturbation, that's something where I could prove exponential decay of some notion of correlation functions right off the bat, just by something like a polymer expansion. So maybe you can ask the question again, because I don't think I got it.
Well, I was just wondering how to recover it from the exponential decay from the tensor RG map. How, anyway, maybe it's.
I guess my answer is that you've already got it even before you do the RG map, because you're starting with something that's already high temperature on which you could do expansions. Now an interesting question would be, start with an Ising model that's in the high temperature phase, but is not so high temperature that you can do a high temperature expansion yet.
Yeah.
See if you do 10 steps of the RG transformation and drive it down to something where the perturbation was now small enough that you could apply the traditional high temperature expansion methods. So maybe you could use it to sort of expand the range in which you could do rigorous high temperature expansions by that sort of program. But certainly haven't tried to do that. My guess is it would be a mess. Well, you'd have to go back in and do really careful estimates on the renormalization group map and just see, because there was a constant in that theorem. It's, the perturbation it's down by a power of 3/2, but with a constant out front. And you probably have to do a lot of work to get that constant to not be, a large number.
So in what you have, if you say computed somehow explicitly the first 10,000 steps, what would that do in your result? Would that help, or would that? I mean, so I imagine it's set up in such a way that you can compute any number of finite steps explicitly, right? If I understood correctly.
Well, what do you mean by compute? I mean, you'd have to.
I mean, you add some perturbation and you apply these transformations, you get your new tensors, and you do this.
I mean, everything is a priori infinite dimensional, so you're going to have to truncate. So yeah, you could compute in the sense you could sort of compute something plus a rigorously controlled error. Is that what you're thinking of?
Well, no, I thought. I mean, maybe I misunderstood. What I thought is that, well, you start with this high temperature fixed point and say you add a perturbation that has, say, only a finite number of a finite dimensional perturbation, and then in principle you could compute a finite number of steps exactly, right?
In principle, I mean, if you start with a finite dimensional perturbation, the number of dimensions as you iterate this map is going to grow quickly.
Right, so 2 to the n or something like, yeah.
Yeah. So yeah, in principle, you could do that. In practice, I don't think you'd get to. I don't think you could do very many steps. I mean, when I was talking about sort of using this to sort of improve the range of applicability of high temperature expansion, I was thinking of doing a computation where you'd sort of carry along an error term that you had bounds on. Because if you really try and compute all the terms, I think it's going to bog down pretty quickly.
Mm. So when you imagine to use this to construct the critical 2D Ising fixed point with it, so you're imagining you wouldn't compute the first 10,000 steps explicitly, but also with error, or?
Well, I would want to start by find an approximate fixed point, find a finite dimensional tensor, which is very close to being a fixed point, and then prove a sort of abstract functional analysis type theorem that says there must be an exact fixed point nearby. Now. And then maybe once you were able to do that, if you haven't retired already, you could look at, say, start with the nearest neighbor critical Ising, and then try and show that that flows to your fixed point by doing something like what you're saying. But I would sort of think the natural starting place is just look for the fixed point, look for a very good finite dimensional approximation to it, and prove there's a fixed point that's a small perturbation of that. Does that answer your question, Roland?
Yeah, I think so. Thank you.
Other questions? Antoine is here, I see, by the way.
Well, if not, thanks again for the great talk.
Well, thanks again for the opportunity.
And see you.
See you.